So today we are going to talk about the automatic speech recognition. It's also known as speech recognition, or also known as speech to text. I would like to give you some of the keywords because today's presentation is not meant to be something very technical. It's more about giving you some keywords in the case that you would like to research more. Then you will have the keyword to start with and the paper. I'm going to give you some papers that are the most relevant one in the case that you want to go deep into this rabbit hole. Is that an expression that we usually? I learned it yesterday, and now I like to use it a lot.
Rabbit hole has a bit of an implication that you should not be going there.
Or
so.
Then it's then the opposite.
Right. Maybe a rabbit tree that you can fly. Now, one thing that suddenly occurs to me is it might be extremely useful if we could record this.
I'm recording this.
You're recording it?
Yep.
Okay. Would you share the recording?
Yeah, definitely.
Okay, good. And also, how would you feel if people ask questions as you go along, or would you rather have them at the end?
Absolutely. I prefer you to stop me in the case that you don't understand. You have no question. So, automatic speech recognition. It's all about. Wait, can I pass that? Oh, can you see it?
Go forward. Let's see.
It doesn't go forward. I don't know why.
Oh no. There we go. This takes time.
It's all about enabling the machines to recognize the user's speech and transform it into the corresponding text. So there are two important things about this sentence: is that we are going to work with speech and that we are going to work with text. So let's take a look at the implications of working with the speech, especially working with artificial intelligence, and working with text. So speech, I know this could be a bit, we are in the speech communication group. I know this could be a bit redundant, but I'm going to say it because it's very important to notice that speech is a massive piece of information. Like only 1 second of audio, of CD quality speech, only 1 second, it's just nothing. It's 44.1 kilo samples. So if I listen to a song, which is, I don't know, a minute and a half, something like this, 2 minutes, it would take, it's a lot of information. It's like reading a very long book. It's like taking a look at an insanely big image. And that's a problem. That's a problem for our systems, memory-wise. And that's a problem for our computation, also the computation and the way we can remember things that happened before that are connected with us now.
And is it possible that there's even more information in the sequence of 1 second? And so that the snapshot that we get is only a part of the information that's about the relationship between samples.
Absolutely.
So it might be even richer than we
currently
are thinking.
Exactly. But it's just so much information. So it's a difficult type of signal to work with in general. Thankfully, I mean, we have some ways to compact this information. We can use the spectrogram, and this is the representation of the time and the frequencies, but very importantly, this can be used as an image. It's something that we can see. Therefore, we can leverage the visual technology that has been, it works very well these days. I guess you have used some AIs to produce images and they work extremely well. We can leverage that to produce sound as well. It's sound that we can see, but then we can convert it to sound that we can listen.
I cannot resist adding, none of you, nor I, can remember a time when we couldn't do that. But for the first couple of thousands of years, when people were studying speech, this was not available. This is amazing. But it's every day now. But we should keep in mind how valuable this is, that you can see it, measure it, and use it to synthesize.
Exactly.
We're very lucky that we came along now.
Yeah, definitely. So these are like the main implications we're working with sound, or at least some of them, but what I consider very important, especially in the automatic speech recognition field. Then we not only have speech, we have text. Text is something that is lined, it's linked with the audio, linked with the speech, but it's not perfectly lined up. It's not perfectly aligned. It's not like a landmark. Landmark is perfectly aligned with the speech, with certain sample in the speech. Text, the only thing that we know is that it's in the same order as the spoken utterance, but it's not perfectly aligned with the audio. And that's very important in automatic speech recognition, because that's a problem. Usually the data sets that we have are some speech, someone speaking, and then some transcription, but we don't have exactly the connection. We just know it happens. All right? So how we used to perform the automatic speech recognition decades ago. We had this part in the right, which is text. For example, it's very difficult to find this sentence, cat sits on a mat. We have some lookup tables. We have some, we can take a look at the Oxford Dictionary and convert these words into phonemes. This is the way it should be more or less pronounced. This is on one side. On the other side, we have the audio, speech, which, as I said, it can be converted into some features. It can be converted into a spectrogram, or it can be converted into the Hebstrom, which is like taking the spectrogram of the spectrogram, which is certain parameters that define the audio, the spoken utterance at certain moment, certain points. And we usually divide the audio into very small windows. We usually work that way because we can consider these windows, if they are short enough, to be invariant, to be something more or less fixed. Because whole speech is something that's changing. But if it's very small, it's something that we can consider invariant. So there's something in the middle that we need to match these two words and sound, which is the acoustic model. So the acoustic model needs to fix two problems, needs to solve two problems. Time, this problem of the alignment that I mentioned, and acoustics. To fix time, we usually work with Markov models. This is states. It's asking myself in which state I am, in this small window, in which state I am, and this state belongs to a phoneme. That is, in which phoneme I am right now in this small window. And the next window, I ask myself the same question. Have I changed the phoneme? Have I changed to, am I in the same phoneme? I'm in a different phoneme. And this is something that is probabilistic because it also depends on the language. For example, in English, if I say T, I'm in the state T, it's very improbable, it's very difficult that I'm going to be in the state L after the T, because it doesn't usually exist in English. If you think in Mexican, in Mexico, in the native language in Mexico, they have TL a lot of times. It's a very common sound. So these probabilities of changing from one state to the other within the windows is something that we can model using a Markov model. And why do we call it hidden? Because the observable, which is the spectrogram, that's the thing that we can see, it's related to something that we cannot see because it's symbolic, the phoneme.
Elizabeth has a wonderful metaphor for this. If there were no people, there would be no phonemes.
Exactly. But this is to fix a problem that we have in time, right? So we can move from one window to the other, and we don't mind the idea that text and audio is not aligned because we have fixed it. But how do we know which acoustic information relates to the phoneme? Because maybe we know that the first phoneme is sh, she just had a baby. But what if I say this. It's not a phoneme, it's a grapheme, but it's a Vietnamese grapheme. I have no idea how this is pronounced. And the machine may not have an idea of how anything is pronounced. That's what I want to exemplify with this example. So we need to have something to match the acoustical part with the phoneme.
Before you go on, can I ask you?
Yeah.
I've never understood this, but I think I might be about to understand it.
Yeah.
So in the step 3, can we express several different likelihoods for several different phonemes? So yes. Okay. So as you go along through the small windows, you might have a place where it's 100% likely that it's the sh, and then another place where it's 50% likely it's a sh, but 50% likely it's the e. Exactly. You can capture that.
Yeah, you have to take the maximum likelihood, because in the end you need to have one. Sure,
but before that, you could actually express the degree to which it's likely to be one or another.
That's true, and that's very important, because this is something that means that it's explainable. It's something that I can see, that I can understand, because I can see the probabilities. So I'm very sure this is this phoneme. I'm not very sure about this other phoneme. This is something that neural networks lack. But continuing with the acoustic parts, we can't have a fixed rule. I mean, look at me, I'm speaking English, but my accent is not like BBC British English. It's something that needs to be, I mean, you can understand me, but there is some variability in language, right? That's why when we don't want to have something fixed, we convert it into something probabilistic, a distribution. If it's something that usually is like normal standard, we use the normal distribution, the Gaussian distribution. But we also know that learning a new language is something difficult. It's not as easy as having just one Gaussian distribution. It's usually a mixture of Gaussians. That's why we use the Gaussian mixture model. And this is how automatic speech recognition was done decades ago, with a hidden Markov model for the time domain, Gaussian mixture model for the acoustic domain. Any question? All right. So, I mean, this is what I just said. This is very quick. This is very cheap. It works quite well. But we know there's now, with the explosion of deep learning, that there exists some other models that may be more precise. However, we need to sacrifice something, and it's explainability. That is why it still makes sense to research this GMM, HMM, because yeah, the neural networks are more precise. Okay, but we don't know what's going on inside. We don't know these likelihoods. We can't know. We don't know what's going on in every window. We can't know. And there's a whole field of research of people trying to understand what's going on in the neural networks. And they, as far as I know, they don't get anything very clear. But now, for now, let's move to the deep learning world. Yeah.
When you separate out time and acoustics, I'm used to thinking of acoustics as having a time dimension. By time, do you mean serial order, sequencing?
Yeah. Okay. It needs to be one window, then the next one. And also because it's Markov model, it means that I don't need to look at the past to perfectly understand what is happening in this moment. All right, so before going to the deep learning world and how to do ASR in deep learning, we need to understand some concepts about deep learning. The first one is the neural network. And this is very simple. A neural network is a mathematical algorithm that learns patterns. That's all. There is no intelligence in artificial intelligence. It's just learning patterns that exist in the reality. How do we show this algorithm what are the patterns that they have to take a look at, that they have to learn. We have some data that represents the reality, and we show examples to the algorithm. That's what we call training keyword, training the neural network, showing examples. The bigger the data, the more examples, the more correct the patterns it's going to learn related to the reality. The smaller the data, then it's going to learn some patterns, but it's not going to apply to the rest of the reality. That's what we call the overfitting. It's another keyword. If it's too overfitted to certain data, maybe it's not going to apply well for the rest. So they usually need a lot of data. And to have visual clue, I'm going to include in the right, in this column, some icons that relate to every concept that I'm going to be talking about. So this is like the brain, what powers everything, learning patterns. Then, if I told you that we usually work with spectrograms, and I told you spectrograms can be considered an image, we need an eye, something to see. And in a neural network, we see using convolution. Convolution is another mathematical algorithm that takes several pixels, that is a small patch of the image, and understands everything. That means it understands very fine details, but it can't understand the whole image. That's not how eyes in deep learning work. They need to understand only a small piece of information. All right? So this is a problem. We can understand fine details, but whenever the image is very big and sound is very big, we need to have another way for working. But yeah, we can see more or less. This is like having a magnifying glass. That's the name of, yeah. Mm-hmm. So we need something to understand the context. And this is in deep learning, we use something that is called memory. It depends. We have two different ways of approaching this. Imagine that I'm working in one window. I understand everything. Then I have an output, a phoneme. This output, I can input it into the next window. That's called recursion or recursive neural networks, RNN keyword. Or we can have a mathematical algorithm, a bit more complicated, to perform this memory, which is called the long short-term memory, which is a mathematical algorithm for learning something, for remembering, forgetting, or letting the information pass. But you need to trust me in this point. We have some algorithms to perform this, but they tend to forget things that happen far away in the time. We can use them to remember something that happened just before, but long-term memory, it doesn't really work. Yeah.
How big are these memories?
The eye, you mean? This one? Or what do you mean?
Well, like when you say that one time window, you get one time window and calculate something that has not the next window.
Mm-hmm.
In speech, how big are these memories?
Usually 25 milliseconds.
Oh, okay. So, it's pretty big.
Yeah, it could be smaller. I mean, that's what I've seen very often.
Okay.
And I don't have an answer. If you are asking how many windows we can remember, we don't know. We can't know. It's not like from this point I forget. No, it's more like it's committing some errors now. So you shouldn't trust this much. That's what I want to say. For the long term. For the short term, you should.
So you're saying like errors will carry forward?
Well, not exactly. I mean, if you need to remember something that's something that you remember is wrong because it happens so far away, then you're going to have an error at this moment because of that.
Am I right, Jen, that your question was about the size of the analysis frame?
Right.
Yeah, So we're used to thinking in terms of 5 or 10 milliseconds. So you're mentioning 25?
Yeah, it depends on the model.
It depends on the model.
Yeah,
I see.
it can be more precise, but
I think as a time cost, I think gradually goes away, but and you can actually adjust it, but you can't really control it. That makes sense.
so if we have this problem with the long-term memory, we can have a solution for that, and this is what has revolutionized the AI field from 2017 when one paper appeared, which is the concept of attention. Think it this way. Do I need to remember what I learned when I was 15 in my geography class in high school for this talk now? No. I need to remember what I learned in my PhD about automatic speech recognition, or at least I should. This is the same concept. Another mathematical algorithm, we are not going to get into the details, but that's the idea. Where should I look? What do I need to remember well for this kind of information, for this window that I'm working on?
Is this something like the concept of usefulness?
It could, yeah, it could be.
Because attention as a concept is you might be paying attention to non-useful things.
Agreed.
They're not exact. So in this framework, attention means deciding or having decided that what you're going to focus on or make use of is actually going to help you.
Yeah,
Okay.
exactly. But it's something that you can learn, that neural networks learn where to pay attention. Because it's useful, but also it's very difficult to know why is it useful. I mean, in this sentence, for example, that it was invented, this algorithm for translation. Can you help me translate this sentence? Can do me helfen diesen Satz to übersetzen? Well, I don't know, I don't speak German. But you know that translate is connected to the last word, but it's not the last word in English. Diesen, it's connected to these, but it's not. That's why we need to pay attention to different places in the sentence. Same idea with the audio. In this case, it's very obvious. Why do we have to pay attention in this and to this? Because it's the same. But in audio, it's not that clear. So we miss some explainability in that sense. But that's how we fix the general memory. Now there is a last thing that we need to take into account. It's how do we tell the model that everything that the model is doing is right? That's what we call the cost function. And this is a very important cost function in automatic speech recognition, which is the CTC, Connectionist Temporal Classification. And it's this idea, it's quite simple. It's that for every window, we are going to predict a grapheme. And if there are several graphemes that are repeated because it lasted longer, it lasted for several windows, we are going to collapse them to only one. That means that we don't need to have states like in the Markov model. That means we just can have a result for every window and then collapses.
Elizabeth, is this related at all to Christine's alignment algorithm?
It's related, but
Maybe faintly. No, it's not the same for sure. Maybe faintly related.
So this is everything that we need to know. Now let's learn about the automatic speech recognition using deep learning. So we are going to learn it from the very beginning, in the moment in which deep learning improved the results of the classical way of doing it, that we already know, which is 2010, in which they changed the Gaussian mixture model for a neural network, a very simple one. You have there the paper, Context-Dependent Pre-trained Deep Neural Networks, in which they improved from a 27.5 word error rate to an 18.5%. And the idea is that the neural network is going to have as an input the window, and it's going to have as an output the probability for every phoneme that we can consider. And we are going to take the highest probability. And this improved because this neural network now, thanks to the more computational power that we can use. They are deeper, they have more intelligence, let's say, and now they improve the results. But of course, I don't know what's happening there. It's non-explainable, but it works better.
I've seen the word NFCC so many times.
It is, these are the, I don't know what they stand for them. Exactly.
Well, frequency means take the spectrum, but you weight it differently. So you split it into pieces, levels, but you put no weight on the bottom because that's where it makes the information. F1, F2, all down. Give it up to 6,000 hertz, there's not much going on. So you split the lower levels and define the details, and then the higher up you go, you just say this region. Yeah, the bands are small at the bottom and big at the top. So that's no frequencies. And capsule coefficients is, as Mateo said, the spectrum is, you take the time signal, right, and you do a Fourier transform, and it becomes a spectrum. What if you take the Fourier transform of the spectrogram? Then you can actually collapse down even more, right? And it has certain properties that we like. For example, the smooth part of the spectrum becomes the low frequency capsule coefficients, and the fast changing parts of the spectrum becomes the high frequency capsule coefficients. So you can, it's a representation of the spectrogram in a much smaller space.
So is the low frequency analysis happening before or after the 6 before?
So you do a filtering of the original and you kind of warp it, and then you get the low frequency spectrum, and then you take the capsule.
Because I've seen MXCC in so many different papers. I'm wondering, is there a reason why we don't use any? Or should I consider using?
You are indirectly using them with the processing that you do. It's a different representation of the spectrum, but we use it in the check.
I see.
The processing is capsule coefficients are a transform. You are doing your own transform.
Oh, I see.
We don't have to do like done.
Thank you.
Yeah, maybe one of these things I'll do. Usually to speech. You have that, but you guys know. I sometimes do a 2-week session and speech policy.
So this improved the performance, but then researchers kept working on it, and in 2013 they decided that, I mean, this is working, every window is independent from the other. But that's not true. Windows that are together usually have information that are related. Therefore, we need to include memory. As I told you, the recursive or the memory model is the one that now we include in the neural network. And with this, we get an improvement of around 20% of the results of the prior work. Just by including this idea of short-term memory from the previous windows.
Where R stands for recurrent.
Yeah, recurrent neural network. Yeah, recurrent. Yeah. And then so the research kept going, and as I told you, maybe there is a like researchers thought about the idea. All right, we are still using the states model. Am I in this state? Should I move to the next one? The probabilities. Maybe we can change it to something else, because in this type of models we need to have an output for every window. But what I would like to have is final sentence. That's the final result I'm looking for. That's why they decided to change to the CTC. You remember? The connection is time classification cost function. And in this way, they can stop using the Markov model. That was maybe a bit more, I don't know, yeah, having an output in every window, maybe it's not the best idea. And then we have this idea of collapsing the graphings in the end. And now we can tell the model, okay, you're doing fine. If the word that was contained in the spoken utterance was hello, you are not doing fine. If it was not that word, you're just wrong. And then the model adjusts itself and gets to a better results. I don't have the numbers, but I think they improved. Yeah, well, and you have here one of the most important papers in that, the deep speech. But then this is 2015, and in 2017, the paper that changed everything, I consider it the best paper that we've ever had in artificial intelligence, with a very strange name. Attention is all you need. That was the name. Invented the idea of attention using a very specific architecture called the transform. And I have pasted here an image of the transformer, because instead of this being a keyword, this is a key image, because you're going to see it everywhere. The idea of having on the left an encoder, on the right a decoder, an input to the encoder, an input to the decoder, and output only in the decoder. You will see it everywhere. And this leverages two ideas. The first idea, it's the encoder-decoder. Encoding means to reduce the dimensionality of something. Think it this way. We have the music in an instrumental piece in an orchestra can be encoded in the paper that the musicians read. This is information that is very useful. We have notes, we have rhythm, we have timbre. This is what they read, and they decode it back into music by decoding the movements of their arm or the positions of their fingers. So this is the same idea. We encode some acoustical information in the encoder into something that, instead of being a paper with notes and rhythms, it's what we call the embedding, because it's not human readable. And this embedding has enough information to decode it back into something that is useful. Instead of being movements of my arm, it's text. So we have automatic speech recognition. It's very important, the word embedding, the output of the encoder, because it's a keyword. You will also see it as a latent space. That's also another keyword. They call it embedding or latent space because they have no idea what it means. It's just something that works. Again, it's something that it's not explained.
What did you call it? What kind of space?
Latent.
So, like a Latin square?
Not latent.
Latent. Oh, sorry.
Got it. Okay, thank you.
It's hiding something that works, but we don't know exactly why. I mean, we can do some computations on this latent space, but it's not as clear as having a note in a pentagram. Do you call it pentagram? Oh, maybe. Yeah.
The school.
Oh, staff.
Oh, all right. So that's the first thing. They use the encoder-decoder fashion, which is this idea. And they use the second one that I told you, the idea of attention, which is what I explained before. It's a bit more complicated than just paying attention. It's some mathematicals involved, but it's this idea. So the decoder knows where to look in the encoder embedding, and based on the inputs, it will create the next word. It works in an autoregressive way. That's another keyword. So if I input cat, it will output sits. If I input cat sits, it will output on. Cat sits on, cat sits on in a mat. That's the way they work.
Oh, wait,
Yeah, maybe that was
sorry.
weird.
The paper is going like this. It's
Yeah.
moving around, and then the input embedding is like the signal of the next word mat.
So the encoder is going to see just the acoustics. Just
of
the
what-
spectrum
of what?
of the word that has this transcription related to.
Oh, so it's transcribing the input
Yeah.
based on the previous output.
Yeah, it uses the audio and it uses the previous outputs. Yeah,
Okay.
Together.
Oh.
together at the same time. That's why it's connected on left. It's like I'm giving the context,
Yeah.
but then I'm predicting the next token.
Mhm.
Next. That's and this is what works extremely well. Extremely well and has revolutionized everything. This is ChatGPT. This is Suno or Udio to generate music. This is AlphaFold that won the Nobel Prize. This is everything, and automatic speech recognition as well. Oh, sorry, I forgot this slide. Yeah, predicting the next word, maybe it's not the best way to do it. So I don't think this is the final architecture that we are going to have in the state of the art. But for now, it's the best architecture that we have.
Was this transformer paper, was the context for speech recognition or was it like a general context?
Translation,
Translation.
text to text.
Oh, text to text.
Yeah.
So, sorry, where does attention come in here?
It's after we have encoded the information, acoustical information, we have something here at the output, which is the embedding, which is the
Right.
small representation of the important features of this acoustic. And the decoder is going to take a look at the parts of the embedding that are relevant for the next token, for the next word.
I see. Is it that? Oh, so you're paying attention only to the.
Only to that, only to the things that are relevant.
It's like kind of like the cocktail problem where you're only paying attention to like the relevant.
Only the relevant part.
I
Yeah,
see.
exactly.
Hmm,
Because this is the whole signal.
I see.
So here I have text on a mat, but maybe for predicting, I cannot. Maybe for this S, it's needed to pay attention for the previous T because it has a stop, closure, stop, something like that. Or maybe for the. See, this is very difficult to explain.
Yeah. It feels like a black box.
It is a black box.
Yeah.
It is.
But I guess I don't really understand how the black box is created, or like how do you train a transformer?
How do you train it?
Right.
Well, you have.
Or maybe this is too much. Maybe I'll go read the paper myself.
It's a good idea. Anyway,
Yeah.
probably.
Yeah.
So you have to show it a lot of examples.
The gradient descent.
Yeah.
It's this modified gradient descent everywhere.
Also, there actually is some sort of model behind. Like you do have to train.
The parameters.
Interesting.
That's yeah, it has a lot of millions of parameters.
Wow.
You have to tune them, and we have some different ways to do it in a very fast way, especially using GPUs, the ones that we use for playing video games, and big data sets.
The cost function, you want to minimize the cost.
Mhm.
So you keep feeding these things and then you adjust the parameters to the cost. That's the math.
I see. Well, what's interesting to me is that the computer doesn't even know what the encoder is.
What the embedding, you mean?
Yeah, sorry, the embedding like between the encoder and the decoder, because you said that it's like something that we don't really know.
That as humans we cannot understand. The computer does, of course.
What do you mean by as soon as we cannot understand?
So, for example, I'd like to explain this also. Like, imagine this is a cheat sheet for an exam. You have the book, but you want to encode all the important information that is going to let you pass the exam. This is something that you can read because it's written. But imagine the computer needs to do this. It would be something that we cannot read. It's just zeros and ones, right?
Oh, I see.
It's not directly linked to something that we can understand.
Yes.
And it's not like encoding, for example, the rhythm of sound. It doesn't exist a variable that means rhythm.
I see.
It's just a variable that means acoustic information.
I see.
But this variable means something different than this other one. But everything makes the cheat sheet.
It's a map thing, but there is no real structure to the map.
Exactly.
Like there's no mathematical formula.
No, no.
Let's do one that just follow the bits and see where.
Oh, I'm fine. Thank you. Wow, this is cool. This is cool. Thank you.
The step that you described that intrigues me so much is, and then we adjust the parameters. Is that a random process, or are there some principles as to what you do?
It's pretty straightforward, actually. You just compare what you want the output to be versus what it is right now, and then you find that cost function, and you see how different they are.
Yes, that's a measure of how much you need to change
Right.
something, but the direction of change.
Right, and then the back propagation, you take that and you put it into the level that was right before it and see how you can change that to more closely match
Yes.
what you want, and then you change that.
Yes,
Because you know where the direction is.
you know what direction you want to go
Yes,
in,
right,
but you don't know, unless I'm missing something, the nature of you don't know the direction of the change that you need for each parameter, or do you?
Yes. Yes, there is a way to feed back the information that you got from the cost to each one of the parameters that led to that cost. And then you keep going backwards in time.
Is it something like this? You know all the parameter values at T1, and you know all the parameters at T2, and you want to make parameter 1 be more similar. You want to change, reduce the disagreement, so you know you have something along this. Okay, all right. Because I think we as human beings are really good at trying to figure out what we would need to change in order to make our behavior better. So if we are learning to speak a second language and we get our vowels a little bit wrong, we don't just randomly change our vowels. We know what to do with our mouth to make it more similar. And it sounds like this approach has some of that capacity.
I think that's why it's so powerful, because
I see.
it matches itself to the problem.
It doesn't just flail around.
Right, so that's why it's called artificial intelligence, because it's trying to map the information that it's given into the parameters, and it's trying to get it as close as possible.
Yes, but you can imagine a different way of attacking that problem that was not very intelligent, that just involved random changes like evolution, theoretically. But it doesn't work like that, you're telling me.
It's more focused.
Yeah. It used to work like that before developing the gradient descent.
Training the HMMs was kind of
Say it again?
Training the HMMs was kind of like
Was
that.
kind of like that, yeah. Okay.
Well, a little better than chance, but this is much more focused.
All right, so this changed everything, and since 2017, but especially 2020, we can see there is a lot of papers, very important papers, that use this technology for different purposes: speech synthesis, speech translation, or in our case, automatic speech recognition.
Wow, these are all very recent.
Oh yeah, definitely. This is 2023.
Because I mean, like I have taken classes that uses Whisper.
Yeah.
So, but that was like 3 years ago.
Yes.
Which is really crazy, yeah.
Because it's changing so fast.
Yeah.
This is a survey from 2023, and this is super old. Just joking, but I mean, some of the most important papers, I would like to point out two. We have Whisper and we have Wave to Back there. I'm going to explain both of them. So Whisper, see the image? It's exactly as I told you. This is exactly the same image. Something in the left, something in the right, some two inputs in the bottom, and one output in the top. But look at this, trained with 680,000 hours of annotated audio.
And how do they annotate it?
It's because they use public databases, like for example, YouTube or videos that some people decided to transcribe, or for example, parliaments, they have the transcription and it's public.
Okay.
But it's not something that they had people annotating. It's that they did their best on this, and probably part of this audio is not well annotated.
It's the word level.
It's a word.
Yes, so tagged means transcribed.
Yes.
That's the word level.
Yeah. Oh, sorry, I'm running low battery. I'm going to go fast to put my charger.
Okay. So is this making any kind of sense? Part of it anyway? Yeah,
Yeah, that's it.
but it's really directly relevant to your thinking, isn't it?
Yeah, I've never, I had taken like the intro ML class before, but I've never had an ML mindset. Also, like, they change the course content every semester, so we never learned about transformers when I took it. So this is, I think, I always say in my talks with other professors that our method is better than neural networks because they're too complicated when we're trying to simplify it. But I think now I understand why I'm saying that from like
Exactly.
understanding
It's clarifying, isn't it?
It's very very good. Thank you.
I mentioned these things, but I never tell you
Yeah.
what it actually is.
Yeah.
Because I'm mystified. I don't know.
Thank you.
So we were talking about, the whisper model. Yeah, the important part is everything is as I told you, but it's trained on massive amount of data, which is transcribed. And it is also multilingual. It is also, it performs transcription, translation. It is very fast. It is very precise. So this is a state of the art. And it's open source. So you can use it and fine tune it.
And when you say precise,
Mhm.
is that about error rate? What is precise in this framework?
Word error rate.
Word error.
Different for different languages, of course. So English, it's like the third language with the least error rate. The first one is Spanish, and it has less data to be so among these 680,000 hours. I don't know which percentage of data is in Spanish, but it's the most. I don't know, this is just a fun fact.
Do I understand you to be saying that the word error rate is not related to the size of the proportion of the training hours?
No,
not
it's
related.
not. It's not.
Interesting. So it's related to something else.
And then what happens if we don't want to have so many hours of transcribed audio? Well, we can take, for example, the approach that Facebook's Meta's model Wave2Back took, and it's training with a big data set of non-transcribed speech in a different task. That is, imagine that instead of transcribing, we would like the model to recover some parts that were missing in the speech. For example, I hide some of the speech, and then I ask the model to recover it. Therefore, I don't need to have some transcription. I just need to have the audio, and then I just need to hide some parts. I have some zeros here, and I ask it to recover it. Then the embedding, the acoustical information that is encoded, it's going to understand perfectly how the audio, how the speech works. It's going to be encoded there. And then I just need to fix the encoder, use this encoder, and with a very small set of data with it, which is transcribed, train the decoder. And therefore, this part, the left part, the encoder, since it's very good, I don't need to change it. I don't need so many data to learn the patterns. And I just need data for this right side. So since it's smaller, it's just half of the model. It's not like that, but it's half of the model. I need less data to learn the patterns, important patterns for transcribing.
Could I ask you, does it matter whether the 60K hours are kind of homogeneous, like from one speaker or something, or does it not matter?
It doesn't matter, and it's also desirable to have different speakers, different languages, different ways of saying words.
It doesn't over.
Exactly. This is 2020. And well, that was everything I wanted to talk about, the automatic speech recognition of text. But what happens with landmarks? Well, we have given a try to using a transformer to predict the landmark position. I'm sorry because this is in Spanish, but the green dots are the original places where the landmark was located. The red dots or crosses is where we have predicted the landmark. And it's a 99 something accurate. This is, again, as we talked Tuesday, if you remember, this is preliminary results because maybe there is some bug, maybe there is something that makes the things look too good because this is very accurate and I'm not sure, but I have sent this to Jose Luis, my colleague in Spain, and he's taking a look as well. And another question that I had is, now that you know the attention mechanism, is the attention related to the landmark position? I don't expect you to understand anything on this image because it's very messy, but we can take a look afterwards. But the answer is it's unclear. But we are still working on this, and previous to this seminar, I was talking with Jose Luis, and he found this especially relevant, and we are going to take a look next week. And last, if we need more data, can't we use the articulatory models we have some models for producing speech that are related to the articulatory positions, which is like this one. This is a representation of one of them. Can we use them maybe to have more data? Because we have, in this case, two approaches. We have some data sets that were recorded in a magnetic resonance imagery context. So we have the position of the vocal tract and we have the acoustics. And in this triangle, we just need to connect the landmarks. Or another idea is that what I studied during my PhD is keyword articulatory copy synthesis, which is trying to mimic what someone said using this vocal tract by minimizing the difference of the spectrum. In that way, we will get, again, the articulatory parameters and then landmark. But this is, I've talked again with Jose Luis about this idea, and this is super crazy idea, very difficult. But well, I just wanted to mention.
Difficult doesn't necessarily mean wrong.
Oh yeah, absolutely. But unfortunately, I'm going to be just 4 months or 5 months. I don't think I will have time to do something like that. No. And that was everything. This is how just what we just seen. We reviewed the considerations when working with audio. We understood how ASMR was done in the past. Reviewed the deep learning, understood the key architectures, presented the key open source models, and the ongoing research. Now it's up to you to decide if it's interesting or not. That's
Oh, thank you.
Thank you so much.